Now, in making comparisons between the planets, we first need to take a global look at the planet Earth and ask, what about it would be of interest if we were, say, a Martian? For each terrestrial planet, we can divide the planet's properties into its surface, its interior, and its atmosphere. So we'll start with the Earth. Earth's beauty is revealed from space through the blue seas, the green jungles, the red deserts, the white clouds. And from our detailed knowledge of Earth, astronomers hope to understand what properties shape other worlds. Earth is a dynamic planet with its surface and atmosphere having changed over its lifetime. Slow and violent motions of the Earth arise from heat generated within the planet. Volcanic gases accumulate over billions of years, creating an atmosphere conducive to life, which in turn, together with water, affects the air's composition. Now, in simple terms, the Earth is a huge rocky sphere spinning in space and moving around the Sun with a speed of about 100 miles a second. Earth also has a blanket of air and a magnetic field that protects the surface from the hazards of interplanetary space. The Earth is large enough for gravity to have shaped it into a sphere. More precisely, it's in an oblate spheroid. If you've ever been on a merry-go-round as a kid and you got the thing spinning as fast as you could, you know it's really difficult to pull yourself towards the center, but it's not as difficult to stand up and down. So consequently, gravity can squish the Earth flat, but it has harder time pulling it in from the sides. So it's slightly shorter than it is wide. This is going to be true of lots of other planets and stars. And one of the most obvious features of the Earth is the fact that its surface is constantly changing and being eroded. Among the causes of erosion are water. The Earth is the only planet with liquid water in our solar system. Atmospheric erosion due to winds, rain, snow, and ice. Life, including us, although trees are the biggest form of life. Volcanoes, and plate tectonics. The continents actually move around on the surface. Now, major changes occur only every 200 million years or so, which is a comparatively short time compared to the lifetime of the Earth. It's the collision between continents that give rise to the mountain ranges, earthquakes, and volcanoes. The most common elements of the Earth's surface rocks are oxygen, actually by mass, silicon, aluminum, iron, calcium, and magnesium. Silicon and oxygen usually occur together as silicates. Ordinary sand is the silicate mineral quartz, and is nearly pure silicon dioxide. So it's one atom of silicon and two atoms of oxygen. Now, density, again, is a measure of how much material or mass is packed in a given volume. Typical units of density are grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter, and surface rocks have 3 grams per cubic centimeter, and iron and metals are much heavier. Iron is 8 grams per cubic centimeter. And for a spherical object, mass m and radius r, the average density is mass over 4/3 pi r cubed. That's the volume of the sphere. So calculating that out for Earth, the density is found to be 5.5 grams per cubic centimeter on average. So consequently, the Earth's interior, or core, probably is iron, which is abundant in nature and high in density. Now, how do we know what's going on in the Earth's interior? Well, earthquakes generate seismic waves that move through the Earth with speeds depending on the properties of the material through which it travels. So the speeds are determined by timing the arrival of the waves at remote points on the Earth's surface. And we can get a seismic picture generated of the Earth's interior along the path of the waves. So what we're really doing is making a sonogram of the Earth. So if I have an earthquake here that's generating waves, at this point, if I measure them, the waves have traveled through this part of the Earth. Where at this point, if I measure them, they have traveled through the center of the Earth. This is the only way we have to probe the deep interior of the Earth's surface. Now, seismic waves have two types, S and P. P waves compress material and travel easily through liquids or solids. P waves are like if I had a slinky and I compressed it and stretched it. S waves move material perpendicular to the wave direction of travel and can only go through solids. Now, if we look at the results after any earthquake, we notice that P waves but no S waves are detected on the opposite side of the Earth from the earthquake. That means that the Earth has a liquid core. I get P waves and S waves, P waves and S waves all the way until I get to the shadow of the core, and now I get P waves but no S waves. So thus we are able to probe the interior of the Earth, and we get a structure. First we have a solid, low-density, thin crust made mainly of silicates. Then we have a hot, thick, not quite liquid mantle with silicates. Next we have a liquid outer core with a mixture of iron, nickel, and perhaps sulfur. And then a solid inner core of iron and nickel. Now the Earth is layered in such a fashion that the densest materials are at the center and the least dense is at the surface. And this is called differentiation. Differentiation will occur in a mixture of heavy and light materials if these materials are liquid for long enough time in a gravitational field. So since the Earth is differentiated, it must have been almost entirely liquid in the past. Earth's inner core is solid because it's under such high pressure that the temperature there is not hot enough to liquefy it. But that's not the case for the outer liquid core. Now we can understand differentiation if you've ever eaten mint chocolate chip ice cream. Say you were watching your favorite movie and you get some mint chocolate chip ice cream and you leave the ice cream on the counter and forget about it until the next morning. You come out and it's all melted. If you were to look at that, you would notice that the chocolate chips, which are the densest material, are all on the bottom. And then there would be different liquids that would be there. You'd have this mint chocolate chip foam up on top. The lightest material is up at top, and the more dense and the most dense on the bottom. Now, as the Earth formed, if I have iron and rock that are all mixed, they would still be all mixed like this today if we were undifferentiated. But if we get heating, and so the rock and iron starts to melt, the iron is going to sink to the bottom and the rock is at the top, and we get a differentiated planet. We're going to see all the planets are differentiated in some form. Now, it's estimated that the Earth's core is about 6,500 K. This high temperature is probably due to at least the following two causes. Heat generation from the impact of small bodies that eventually form the Earth by their mutual gravitation. So as they struck, every time lots of energy is given off, it heats things up. And the radioactive decay of radioactive elements that occur naturally in the mix of materials that make up the Earth. In either case, the thermal energy generated is trapped inside the Earth's interior due to the long time it takes to move to the surface and escape. And the Earth has a high surface area to volume ratio, which means it takes a long time for it to cool down. Just like a block of ice takes much longer to melt than different ice cubes. The ice cubes have more surface area and melt faster. So the less surface area to volume ratio you have, the more time it takes to melt or cool down. Now we can also determine the age of the Earth using radioactive decay to determine the Earth's age. Radioactive atoms always decay into other types of atoms. We call those daughter atoms. The more daughter atoms there are relative to the original radioactive atoms, the older the rock is. In particular, we could look at potassium in rocks. Radioactive potassium has a half-life of 1.28 billion years. That means if I had, say, a pound of it, 1.28 billion years later, you would have a half pound of it, and the rest of the mass would be in other daughter atoms. So every 1.28 billion years, half of the potassium disappears. And potassium decays into argon and calcium. Well, argon is a gas that will be trapped in a solid rock, but if the rock is liquid at all, the gas will bubble out into space and will no longer be in the rock. So, We can assume the rock has no argon when it originally formed, when it went from a liquid state to a solid state. Measuring then the ratio of argon atoms to potassium atoms gives us the age of the rock. And this method gives a minimum age of the Earth as 4 billion years old. Now, in science, we don't really trust single measurements. We make lots of measurements. And so when considering the age of the Earth, I've given you an example of how we would age the Earth, but there's many more different scientific tests that we can do. And you put all those together, we get an age of about 4.5 billion years old. Now there's some motion in the Earth's interior. Heat generated by the radioactive decay in the Earth creates movements of rocks, and the movement of materials called convection. Convection occurs because the hotter material rises up because it's less dense. As it cools down, it becomes more dense and sinks back down to the bottom. So the crust and mantle are solid rock, although when heated, rock can actually develop convective motions. And the convective motions are very slow, but are the cause of earthquakes, volcanoes, the Earth's magnetic field, and perhaps the atmosphere itself. So convection causes some different things with plate tectonics, and one is something called rifting. I have hot material from down below finds itself in a great slow plume that works its way up to the surface. As that works its way to the up, it drags the material around it in these convective cycles. Well, where it's coming up, as the material comes out along the crust, it actually pulls the crust apart from each other and makes the oceans wider. So that stretching of the crust that spreads and breaks the surface is a phenomenon called rifting. Now, on the other side of this convective zone, we get something called subduction. So as the cool material sinks, it drags the crust under another area that's maybe moving towards it. So it causes them to buckle upwards and cause the mountains. So if one piece of the crust slips under another, the process is called subduction. Rifting and subduction are the dominant forces that sculpt the landscape. They may also trigger earthquakes and volcanoes. This picture here is the picture of earthquakes over the course of a year. And we can see that they occur in patterns and lines across the surface of the Earth. They essentially are on the edges of the plates. And so we see then the plate structure of the Earth by looking at where the earthquakes occur. The shifting of the large blocks of the Earth's surface is called plate tectonics. Early researchers actually noticed that South America and Africa appeared to fit together and that the two continents shared similar fossils. It was later proposed in 1912 that all the continents were once a single supercontinent called Pangaea. The Earth's surface is continually building up and breaking down over the timescales of millions of years. Next, I want to talk about the Earth's atmosphere. So a veil of gases around the Earth is its atmosphere. And relative to other planetary atmospheres, the Earth's atmosphere is unique. However, studying the Earth's atmosphere can tell us about atmospheres in general. The Earth's atmosphere is primarily nitrogen, about 78%, and oxygen, about 21%. The remaining gases in the atmosphere consist of about 1%. That's carbon dioxide, ozone, water, and argon. Those first three are very important to life. This composition is unique relative to the carbon dioxide atmospheres of Mars and Venus, and the hydrogen atmospheres of the outer large planets. There are several theories to explain the origin of Earth's atmosphere. The release of gas, which was originally trapped when the Earth was formed by volcanism or asteroid impacts. And also materials brought to the Earth by comet impacts. Comets are mostly gas, ice made out of different gases, and as it strikes, it heats up and melts, and if we have enough gravity, we can hold on to that gas. The early atmosphere is much different than it is today. It contained a lot more methane and ammonia. But as the sun started to shine and it gave off lots of UV light, it was very intense, and that breaks the hydrogen out of the methane and ammonia and out of the water in the air, leaving carbon, nitrogen, and oxygen behind, while all the hydrogen escaped into space. The Earth does not have enough gravity at our temperature to hold on to the hydrogen. Ancient plants further increased the levels of oxygen through photosynthesis. The oxygen in the atmosphere provides a shield against solar ultraviolet radiation. O2 provides some, but O3, or ozone, provides most of it. The ozone layer is mostly located at an altitude of 25 kilometers. And the shielding provided by the absorption of ultraviolet photons by oxygen molecules causes them to disassociate. And then the single oxygen atoms recombine with either oxygen or O2 to replenish the lost oxygen gas and ozone. It's very doubtful that life could exist on the Earth's surface without the ozone layer. The other thing that happens in our atmosphere is something called the greenhouse effect. It's not always a bad thing that you've heard in the news. Visible light from the sun comes and strikes the surface, and it's absorbed by the surface and it heats it up. Anything that's hot emits infrared light. The infrared light goes out and some of it escapes, but some of it is absorbed by the atmospheric gases and reflects it back down to the Earth. That traps it and reduces the rate of heat loss and makes the surface hotter than it would be otherwise. Without some greenhouse effect, we would live on a very cold planet. The atmosphere extends to hundreds of kilometers, becoming very tenuous at high altitudes. It also becomes less dense with increasing altitude. In fact, half of the mass of the atmosphere is within the first 4 kilometers. The atmosphere eventually merges with the vacuum of interplanetary space. Now, magnetic forces are communicated by a magnetic field. Direct physical contact is not necessary to transmit magnetic forces. You know that if you've ever played with a magnet and pushed one magnet with the other without them touching. Magnetic fields are depicted by diagrams with magnetic lines of force. Each line represents the direction a compass would point if it was placed in the magnetic field. And the density, or how close the lines are drawn together, indicate how strong the field is. Magnetic fields also have a polarity, a direction from a north magnetic pole to a south magnetic pole. Magnetic fields are generated either by large-scale currents or currents on the atomic scale. The magnetic field of the Earth is generated by currents flowing in its molten iron core. The currents are believed to be caused by the rotational motion and convection, which we call a magnetic dynamo. The Earth's geographic poles and magnetic poles do not coincide. Both the position and strength of the poles change slightly from year to year, even reversing the polarity every 10,000 years or so. Now, the Earth's magnetic field screens the planet from charged particles emitted by the sun. The sun, as we're going to learn later, spits out many charged particles in the form of gamma, alpha radiation and beta radiation. Those charged particles stream outward from it. In this case, charged particles cannot move through a magnetic field line very easily. What happens is it causes the particles to spiral along the magnetic field line. And so it deflects the charged particles into spiral trajectories and slows them down. Then as the charged particles stream past the Earth, they generate electrical currents in the upper atmosphere. These currents collide with and excite molecules. As the molecules de-excite, light photons are given off, resulting in aurora. Just a picture of the aurora borealis, or the northern lights. And all the light that we see is the air molecules that are de-exciting and giving off light of different colors. Auroras can be very beautiful, and they form these long streams, and they change. They're not just a stationary thing. They vibrate and move over the night, and they just can be quite beautiful. Again, auroras are not static. They move over the course of the night. Here's a picture from space of the southern aurora over Antarctica. And it will move. If you want to know when conditions are favorable, there's a good website called spaceweather.com. And you can go there, you can see what's up, and actually it will send you email if you ask for it and saying this would be a good night to look for northern stars, or there's a meteor shower, or there's an eclipse going to be in your area. The region of the Earth's environment where the Earth's magnetic field affects particle motion is called the magnetosphere. And within the magnetosphere, charged particles are trapped into two donut-shaped rings that encircle the Earth called the Van Allen radiation belts. Now, the rotational and orbital motions define the day and the year and cause the seasons. But our planet's motions also have other effects. Basically, it affects air and ocean circulation. Now, let's say I was at the North Pole and I had a very large gun and I was shooting towards this target here off of the coast of South America. Really long distance. As I fired that down, the Earth is actually going to rotate. And so, even though I aimed at this direction, it's going to land over here. So it appears that there is a force pushing it off to the side. It really is due just to the rotation of the Earth. And that apparent curved motion of an object is called the Coriolis effect. Now, it's responsible for things like the spiral pattern of large storms, as well as the direction of the rotation. The trade winds that move east and west in two bands, one north and one south of the equator. The direction of the jet streams, and the deflection of ocean currents that create flows such as the Gulf Stream that carved the Gulf of Mexico. We will see the Coriolis effect in other planets like Jupiter, Saturn, and Neptune, causing this band structure of air moving one direction or another, or causing these storms that form on all the different gas giants.